All right. So we are looking at the respiratory system today. So we're going to be talking about, so if you kind of chart like our progress so far as we've sort of moved through this course, we kind of started by, giving a brief overview of like the idea of metabolism. And then the second day, we kind of went into the digestive system, which talks about how we get some of the ingredients for metabolism. Well, today we're going to kind of finish, continue on with that same conversation where it's like, how do we get part of our fuel source for metabolism? Because yeah, a lot of it is fuel. Like we think of food as fuel for our body, but sometimes we forget that like oxygen is arguably the most important part of the fuel for your body. And you can kind of like rank things in in terms of like their importance and how long you can survive without them. Like you've only got a few minutes without air. You've got a few, you've got a several number of hours without things like water, and you can go a few days without food. Um, but like all of those things are obviously entirely necessary for like the human body to survive. But the respiratory system is kind of a fun conversation because we're going to look at how we are able to kind of extract air and be able to carry that throughout all of our cells through our entire body in order to like be able to deliver that air. And so we're going to kind of look at some of the deeper parts of the respiratory system. I mean, obviously, we've talked about the respiratory system in the past in like our assessments classes and things like that, where we've been like, your breathing efficiency is obviously related to this. Your VO2 max is this. But we're going to look a little bit at the chemistry of like how our body actually grabs oxygen molecules so we can make sense of like, how we actually utilize, carry, and then how do we separate like all the other gases that are in the air as well. So uh, first thing we're kind of break down is just kind of understanding the process of like what breathing is, right? So breathing is more commonly referred to, or at least medically referred to, as what we call pulmonary ventilation. So whenever you see the word pulmonary, we're talking about like our lungs, right? That's our lung system here. So pulmonary ventilation is going to be the process of breathing or ventilating ventilating the lungs. Okay. So like this is the process of like driving air into these big fleshy sacs. Now, again, this is actually very similar to our digestive system in the sense that like this is going to be another weird one to kind of talk about, but this is another human donut analogy. Your lungs are still also technically part of this outside environment, right? Like your lungs, even though they're inside of your chest, are still technically like an outside environment thing. So we need to be able to have a system for getting oxygen molecules from one side of a wall to through that wall to the other side. And so we got to get it from the outside to the inside of your body. We got to be able to drive a bunch of oxygen molecules into our lungs, and then we need to get those oxygen molecules to actually pass into our bloodstream. Now they're inside your body. Now they're systemic, right? Um, so how the heck do we do that? Well, luckily, similar to your small intestine, actually, your lungs have a massive amount of surface area. And you kind of see it and you think that it's like it's only so large. But if you think about like the amount of surface area that your lungs have, your lungs actually branch uh millions and millions of times. So like they come down, it comes down in like one big central tube that branches out into two smaller tubes, and that goes into each of your individual lungs. And then that branches out, and then that branches out, and then those branches branch out. It branches and branches and branches and branches and gets smaller and smaller and smaller and smaller, and all of that increases your surface area until eventually it gets so small and so microscopic that it's covered in these little popcorn shaped sacs. So we look at like bronchi and alveoli. If you look at your lungs here, look at how much surface area this actually is. Imagine again, you want to think of like surface area, and I always think of surface area as like how much paint it would take to like paint something. Like if you didn't have these tubes running through here and you needed to paint the inside and the outside walls of your lungs here, it'd be pretty easy, right? You would just slap a coat out here and then flip them inside out and slap it there. But like because this breaks and there's all this like little pieces inside here, that's you got to paint each individual. There's way more surface area. So it branches and branches and branches, and this isn't even that great of a picture. I should find that one. This is also not showing quite as many branches. This is so very zoomed out. They get so much smaller than this, but eventually they end in these little tiny popcorn shaped sacs, right? And then those little tiny popcorn shaped sacs are covered in blood vessels. And that is actually where the exchange site of oxygen happens. That's actually where, okay, it's official, O2 molecules can actually pass through the wall into the bloodstream, and then carbon dioxide molecules can pass through the wall out of the bloodstream back to the outside environment to be carried up these tubes and out of the body. So that kind of is the general overview of sort of what we're going over today. You can, and then there you can kind of see those blood vessels, right? So we're going to kind of look at what that is. So the primary like purpose of ventilation, right, is just to make oxygen available to the blood. It's to drive in a massive flow of oxygen, let it sit there, and then those oxygen molecules can be attracted to the inside blood, and those CO2 molecules can be attracted to that outside environment. And then that's going to be transported by your cardiovascular system throughout like the rest of your body. So once you've got like all those oxygen molecules, now it's blood cells' job to actually carry that stuff around. That's what we'll kind of get into. I believe tomorrow we'll get into a little bit of the cardiovascular system. So it's funny also as well, and I'm probably going to mention this again tomorrow, but it's funny, we always talk about the heart and lungs together, but they don't actually serve at all like similar functions at all. Like they're totally unrelated in terms of like how they function and what they do, but like the purpose of why they function is obviously, you know, totally interlinked, right? Like your respiratory system can't deliver oxygen to your left pinky toe, which is really freaking far away from your lungs, without a cardiovascular system that can carry that oxygen down there, right? And your cardiovascular system doesn't actually have the ability to supply, you know, the like oxygen and nutrients unless it's able to get them from the respiratory system. So their functions are very different, but they definitely rely on each other in order to like supply your body with all of its needs. So pulmonary ventilation is a big term we're going to see. Whenever you see the word ventilation, we are talking about actually breathing. That's part of the big conversation we've been having in this world right now, right? We've been talking a lot about like ventilators and things like that. That is actually a machine that assists with driving in bulk flow of oxygen molecules. You know, because what this virus does is it basically destroys your ability to like bring that in. You know, that's what a novel coronavirus is. That's what like SARS is, right? Like it's basically a disease that fills your lungs with other materials, making it very difficult for oxygen molecules to kind of get into your bloodstream. So your cardiorespiratory system is very different than just your respiratory system, right? That is where your respiratory and circulatory systems kind of come together, right? So in the way that like these two things are going to sort of like function as a unit, we call that your cardiorespiratory system. And I'm gonna do these notes just a little bit differently, but it's we're gonna put like this bold version as the definition here, and then I'll put, just for the sake of it, two sub definitions underneath. So it's no bolding. Its basic purpose is to deliver oxygen to the mitochondria of these cells, okay? So remember, like mitochondria are where we produce ATP in the presence of oxygen, right? Like we produce ATP in two locations, right? We produce it in the fluid portion of the cell if it's anaerobic, and we produce it in the mitochondria if it's aerobic. And that's where we allow, think aerobic, right? That's where oxygen molecules are allowing ATP production to happen. And so the cardiorespiratory system, if you think of it as like one interlinked system, is really what keeps your entire body's ability to produce energy functioning, right? So you get the respiratory system, which is actually gathering the oxygen molecules, and the cardiovascular system, which is delivering it. And so that's what we're going to put here. I can never get my ITSs right, at least in real time. So the respiratory system is the system responsible for gathering O2 molecules for the body, and your cardiovascular vascular/circulatory, depending on who you decide to ask, system is responsible for delivering O2 molecules throughout the body, right? That is that is kind of like the whole process of pulmonary ventilation. So let's go ahead. Today we're definitely primarily talking about like the lungs and the respiratory system. So we're gonna go ahead and break that down right now. Let's go ahead and talk about like what our actual lungs are, right? So your lungs are these big kind of fleshy sacs that are, you know, really flexible, like they're really kind of able to expand, kind of like a paper bag, you know. Has anybody in here ever had like a panic attack and you've had to like breathe into the paper bag and in and out of the bag? Anybody ever had one of those?
No.
Well, that is fortunate. That is a good thing. It is supposed to be absolutely awful. And we'll actually kind of address that here in just a little bit when I start talking about like pressure. Will use that to kind of help our understanding of pressure, because actually what's happening when somebody's having a panic attack, yeah, it's absolutely related to like you panicking, and like it can be caused by like emotionally. But what's funny is it's actually a little bit of chemistry is what's really causing that to happen. So we'll look at that when we get to talking about pressure here in just a little bit. But that bag expanding, and you know, when you breathe in, like, you know, contracting and then like expanding and contracting, that's actually exactly how your lungs work. So your lungs are attached to, you know, your diaphragm, right? Your diaphragm is this big dome-shaped muscle. It actually sits, when it's in a relaxed position, it sits kind of like this. It sits in kind of a dome shape. But when it contracts, it squeezes and flattens down like this. And what that does, that's kind of like grabbing the outsides of that paper bag and pulling them like this, which expands the amount of space within that bag, right? But when the diaphragm pulls down, like flattens down like this, it pulls your lungs open. And that's what causes air to rush into your actual lungs. And then when your diaphragm relaxes and goes back to this shape, that pushes air out of your lungs. So it's kind of funny because to me, it seems backwards. Like when I first learned this, I was like, that seems really backwards, because like, it seems like breathing in is something that kind of happens when I relax, but I have like a lot of control to go, you know, like really hard. Like I can't breathe in as hard as I can breathe out. And so like the breathing out is the relaxed and the breathing in is the contracting. That seems backwards to me. But breathing out like that is actually a secondary respiratory muscle. That's actually the same muscles that help you crunch and move your spine around, that assist in like that heavy breathing out. Those are secondary respiratory muscles, not your primary ones. So that always kind of surprises people, but like that's, if you think of like how your lungs are shaped as like sacs, it actually makes perfect sense, right? You're basically pulling on the outside part of the sac, and that opens the sac up, causing an area of low pressure, and then air wants to always travel down to an area of low pressure. So in your lungs, oxygen is moved into and out of the lungs through what we call the conduction of your lung tree. So your lungs are going to kind of be split up into two primary sections. One of those sections is what we call the conduction zone. And the conduction zone is basically just creating like an area for all this stuff to happen, right? So like these bronchi, these tubes here, that is part of like the conduction zone, right? And then you have got in each of your lung, you've got what we call your primary bronchi and your secondary bronchi. So let me open this back up here. So at the lungs, oh boy. So your lungs are these large, empty, sac-like structures that are able to house the conducting parts of the respiratory system, right? Primarily, those conduction parts are going to be your primary bronchi, and then you do have like secondary bronchi as well, which can branch down. So you've got what are called bronchi, which are large tubes that conduct oxygen further and further into the lungs. Okay, and then that is going to branch down into your secondary. We'll call it, I guess we should call those your primary bronchi. You're not going to see the term primary versus secondary very often. They usually just, most people just go, you have your big bronchi and then it becomes bronchioles is like usually just step 2. But secondary bronchi, in fact, you know what? We are going to do it that way as well because that's actually how it's presented in your normal textbook. So your bronchi are large tubes that conduct further into the lungs. What will often happen is they will branch. Bronchi will branch into smaller and smaller tubes. And eventually they will become your bronchioles, okay? So we'll say that here. Eventually branching so small they are considered bronchioles, okay? And bronchioles, which are the small versions, are basically very microscopic branches from the bronchi that house the alveoli, okay? And so these get very, 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 very small until eventually they become like what we call alveoli. So each of those little tiny bronchioles, the end of the tree basically ends in these little popcorn-shaped sacs, right? So this would be a bronchi. Like I said, this would be like a primary bronchi, and then this would be like a secondary bronchi, and then it would get really, really, really small until it looks kind of like this, like this, and then this would be like an individual bronchiole. But that's honestly not how most people break it down. Like your NASM textbook doesn't really break it down that way. It just has like, you know, we consider this like your bronchi, and then the small ones are bronchioles, and there's not really a distinction between like, well, how small does it have to be before it's considered a bronchiole? It's like nobody cares. But eventually the bronchiole is what ends in these little popcorn-shaped sacs here. So technically you can call this like a secondary bronchi, and then finally the individual tube. But there's not like a real classification, like a real distinction, at least on the level of understanding that we need, right? I'm sure like if somebody is like a crazy, like only studies the lungs for their entire life, I'm sure they have even more distinctions. But bronchioles are the microscopic branches, and they end in your alveoli, okay? And what alveoli are, so we got all these like little subnotes here. We can actually kind of see, it's almost like our notes are branching the same way the lungs are, right? So you got the sac, which houses the tubes, which then break into smaller tubes, which then house the alveoli. And these are small, actually not just small, microscopic popcorn, and I know that's kind of weird, but that is actually how most people refer to it, popcorn-shaped sacs that are covered in blood vessels. And act as the exchange site for gases, okay? So this is actually where gases are being exchanged, right? This is where O2 is going to enter the lungs, enter the blood, and CO2 is going to enter the lungs, right? So O2 is now going to be driven into the blood, while CO2 is going to leave the blood and enter into the lungs. And then when you exhale, it'll travel, you know, from that little bronchiole up to the larger junction, then the larger one, the larger one, until eventually it comes all the way out your mouth. And so I always like to think of our respiratory system. I mean, we live in LA, which is full of highways, right? I kind of think of the respiratory system like that, actually. Like you have like a main freaking freeway, which might branch down into like a smaller version. Like if this was like the 5, and that branches off into the 170, which then branches off into maybe some side streets, which eventually becomes your driveway. you know? And so it gets smaller and smaller, like those streets get smaller and smaller and smaller until eventually you end up in those like streets like we have here in LA where you gotta, you're traveling down, you gotta like pull over to let somebody by. Because the streets are too freaking small. Uh, so I mean, honestly, that's kind of how our respiratory system looks. And you can see like it's covered in capillary beds, right? Like look at how many blood vessels are actually covering. We usually draw it like this, but like it is absolutely covered head to toe. And you can see where like the deoxygenated blood is kind of being dropped off and the oxygenated blood is being picked up. And then now that's going to work its way into your bloodstream and travel up to your brain and down to your feet and over to your arms and your digestive system. It's going to go all over the body, right? So when we're looking at like ventilation, right, the anatomy that we've got here, we've got our nose, right, which is a really great, like, very flexible chamber that allows like air to like travel in. It's also like working with your immune system. You've got a little bit of your immune system right there in your nose. That's why you get your nose hairs. They're there to like gather any foreign invaders that might be carrying things that might make you sick. Then you've got like your pharynx and larynx, right? Which your pharynx is going to be the section up here from your nose. And then like your larynx is the part coming from your mouth. And eventually those two tubes combine and travel down what is called your trachea. And your trachea is this kind of it's made of cartilage. It's why your throat is kind of a little squishy, but not really. Like it's very cartilaginous, it's stiff, but it's also very flexible. And so then it'll travel down that, and that's where it kind of branches into your bronchi, which will branch smaller into your bronchioles until eventually they will end in like the alveoli. And so this whole system here is designed to actually like warm oxygen as it's traveling into your body. And we've all experienced that moment where like maybe you've walked outside and it's from inside your house where maybe it's really cold outside and you take that first big breath of air and you're like like it almost makes you cough. That's actually that coughing reaction is because oxygen molecules cannot travel as effectively because the tubes, when you brought in all that really freezing cold air, it actually causes like when stuff gets colder, it shrinks. And so like that caused like a massive constriction. And so then no oxygen was like transported. So your body like coughs and that kind of heats everything up and then it makes it much easier to breathe afterwards. It also moistens air, that little bit of water and like fluid that's actually within that actually makes it easier for O2 molecules to be able to penetrate into the bloodstream. And so like this whole system is kind of designed to create that type of environment, which makes it easier for us to gather O2 molecules. You're also going to see like mucous membranes that filter air as it's coming in and out. So like what they call it ciliated. Cilia are basically like these little hairs. Remember when we were talking about microvilli on Friday, right? They're the little hairs. They don't actually, like villi are what absorb the nutrients, but the microvilli are these little hairs. And like if a sugar molecule misses the right slot, the microvilli kind of they kind of push it up and it's like, there you go. And then it drops into the right hole. And now suddenly it's finally in your bloodstream. So villi, like these little hair-like projections. Well, cilia is the general term for a hair-like projection from a cell. We call like, most animal cells have cilia on them, which is always easy to remember because animals are furry, right? And so like villi are an example of cilia. Well, in your respiratory system, you've also got like a bunch of cilia, and their job isn't necessarily to like make sure that O2 molecules get pushed the way they go, because O2 molecules are very, 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 very small. But cilia's job is actually like if a virus or a bacteria happens to like get into your lungs, their job is to like grab it and kind of hold on to it until your immune system can come along and like eat it and destroy it. So that's one of the really cool things. That's like a mucous membrane. That's actually why you produce so much more mucus when you get sick. That's your immune system trying to like keep any other foreign invaders from getting in there. So it's kind of funny. We think of like the virus as like making all this mucus, which is so annoying and like feels like you're hacking up a lung when you get sick. But that's actually your immune system trying to just make it better at like capturing. If it can just stick a virus like to the ground and make it stick there until like your immune system comes along and eats it, it'll be way easier to kind of get you over that cold faster. So that is kind of, that's a really good overview of like pretty much everything we're going over today, minus we haven't talked too much about understanding like pressure gradients, but we're just about to get there. So that's the other big thing we need to understand. We kind of need to understand the gross anatomy, and then we want to understand like a little bit of the chemistry. So let's go ahead and look at like ventilation, right? Let's break ventilation down a little bit further. Now that we know all the working parts, let's talk about like how we actually breathe. So ventilation, again, if we go back to the top here, pulmonary ventilation is the process of breathing or ventilating the lungs. So we'll give it ventilation. Again, same concept here, right? It is the movement of, and it says air, air into and out of the lungs. So really quickly, we got to kind of talk about like what air is. And I know like, you know, when we think of air, we think of oxygen, right? But air is not just oxygen. In fact, there's actually less oxygen in the air than a lot of other types of gases. If you look at like composition of air, I want a pie chart. Yeah, good job, Google. All right, this is actually what oxygen, I mean, this is what air looks like. It is 78% nitrogen, which is hilarious because we just spent all of Friday talking about how our body consumes amino acids. That's our way of getting nitrogen, which is necessary for our body's production. So it's like, well, if 78% of it is in the freaking air, why don't we get it that way? That's just not how our system is sort of designed to work. But most of air is actually nitrogen. 20% of it is oxygen. A little bit of it is carbon dioxide and other gases, like all that stuff that you exhaled, that's still floating around the air. There's some inert gases like argon out there as well. And then a little bit is going to be like water vapor. There's a lot of like water vapor flying around. I have no reason to believe this statistic is 100% true. But speaking of like things like water vapor, I remember hearing a statistic and I was like, I remember hearing a statistic years ago. And I was like, well, I have no way of knowing whether or not that's true. And I don't have the tools necessary to look it up. But so I don't want to like propagate this possible rumor, but here's a weird fun fact that I heard, you know, on the internet. Obviously, if it's on the internet, it's true. There's so many like fast food restaurants in Los Angeles that like there's a certain percentage of the air that is constantly just floating around hamburger meat and grease and things like that. That probably is relatively true, although not lately. You know, like our air quality has gone up so much in this like quarantine world because so many people are like, so many less people are driving. Los Angeles has got some of the best air quality in the world right now, which is an insane concept when you think about it. But when we say air, we're not talking about oxygen. When we say air, we're talking about gases. We're talking about a mixture of gases, the most important of which, at least in our opinion, is oxygen. So ventilation is bringing air into and out of the lungs. So for air to move in and out, into and out of the lungs, you have to have what is called your intraalveolar pressure. And that has to exceed what we call barometric pressure, okay? Now, really quickly, just giving you a brief rundown on like what pressure is. So, you know, one of my favorite, you guys have heard me say, because it's like, you know, it's like my catchphrase at this point. I love saying like function follows form and form follows function, right? Like we know that those two things are linked together. And if you want to understand the universe, as long as you understand that, you're doing pretty well. But there's another concept that's one of my favorite things to understand. And this is also directly related to understanding how sort of all of chemistry and biology works. And that is this concept right here. Nature hates gradients. Nature does not like it when there is a whole bunch of stuff over here and very little stuff over here. Nature wants it to all be even naturally, right? That's actually even what, like on a certain capacity, that's even what gravity is. Like gravity is basically like a big empty space, and so that is drawing other stuff like towards it. It's attracting stuff towards it to like fill that. That is sort of like nature's goal. Nature always wants to seek a nice, even, like level playing field. So a good way to kind of understand this, and this is actually how like our blood is going to work later on. If you were to take like a semi penetratable membrane, right? So like, let's say you took like a sausage casing, right? Sausage casing, like for the most part, it seems like it's kind of a solid, you know, like we stuff sausage in there in order to be able to eat it. So it seems like it's very like solid, but though there's actually a lot of like little tiny holes within that sausage casing. It's actually somewhat permeable. If something was small enough, it can actually leak from one side to the other, particularly water. If you were to like fill a sausage casing with water, you know, at first you would fill it and it would be, you know, wet on the inside and dry on the inside, but eventually it would actually start, you know, getting really wet on the outside, and that water would eventually leak out. It just happens at a very, 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 very microscopic. You can't really see it happening. It just kind of slowly appears before your eyes. So let's say you took a sausage casing and you wrapped it all up, and you would have put that sausage casing and you filled it with salt water. Okay. And then you dropped that into a bucket of normal water. Well, what would happen is actually all of the water from that sausage casing would actually move. So I can even pull a picture of this up that'll explain it a little bit better. Let's see here, hypotonic versus hypotonic, water. Yeah, we're getting there, and this is where we're headed. We're heading to the blood world eventually. Sausage casing. It's what everybody uses when they show this the first time. They always show like a sausage casing in there. People watching this video are probably like, there's no way he's going to find a picture of that. I'm telling you, this is how everybody teaches it. So take a look here. All right, so you can kind of see, right? You can see like this tube here. Now, there's a bunch of like proteins in here. Oh, wow, this is actually, oh, this is talking about dialysis. I actually don't want that direct picture. I mean, close. Okay, fine, we'll do the, yeah, that's fine. Okay, we'll pull a picture back up. All right, so you have, this is a dialysis bag. This isn't a sausage casing, but dialysis bag, you know, that's how this works. So you've got all of this like normal, you know, high concentrated fluid, right? And then you've got all this other fluid outside here, right? So there's a very obvious difference in the concentrations of stuff, right? So like there's a whole bunch of stuff in this very small space, and there's nothing in this very large space. So what's interesting about that is that all of these little molecules that are trapped in here, they don't want to be in this bag anymore. They want to fill this empty space because nature hates gradients. Nature cannot stand it that there's a whole bunch of stuff here and very little stuff over here. Nature is super OCD and wants to push it to where the concentration of stuff in this bag is the same as the concentration of the stuff outside of the bag. So what ends up happening is these little solutes, these little particles here, are going to move, and then they are going to eventually be the same distance apart as they are inside the bag as they are outside of the bag. So like, see how much space there is between each of these, and then see the space on the inside of the bag? That space is equal now. That is like, and nature's nice and happy. Now it's what we call an isotonic solution. It is able to stay the same on both sides. Now that's one version of what would happen here. Occasionally you'll get the other version, which is where water from outside will actually move inside the bag. And then you'll actually lose water level in here, but then this will start to inflate. And that's doing the same thing. Water rushes in so that it can push all of these particles evenly spaced apart from each other. And that is kind of how pressure works. When there's a lot of space here and very little space here, gases will naturally move to where there is a lot of space. That's why, like, when you see like a science fiction movie, and you know they open up the airlock and it looks like it's like air is just being sucked out of the room, and like, you know, the people in the movie are like holding on to something and they're like being pulled out the door, right? That is because there's just very little air in space. There's just a bunch of empty, you know, space. And so all that air is rushing to fill that empty space. That is what suction, that is what like oxygen movement, that's what that is in a nutshell. So when we look at like pressure gradients, right? When there is, yeah, that's not what I'm looking for. Pressure gradient, high pressure versus low pressure, respiratory system. Yep, there we go. So when we look at like the difference here, right? This has like, there's very little, like there's a lot of volume here, right? There's a lot of space in here. So there's not very much pressure. This oxygen can kind of just hang out. There's not very much pressure. Oops, okay. But if you were to like push down on this, the pressure is now going to increase. So if we go back to our slides, right? If we look at like what the process of ventilation is, for air to move out of the lungs, you have to have pressure that is greater than the air pressure. So like when you contract your lungs, you are basically pushing down like this. And now all of these like little O2 molecules, all these O2 molecules are so close together, nature's like, ugh, gross, all the oxygen's close together. Well, it's way far apart outside of this body. And so what'll happen is all the oxygen will naturally rush out of your lungs. All of the air will rush out because there's so much pressure until eventually when you're done breathing out, the pressure in like the air of the room that you're standing in and the pressure inside of your lungs is equal. Or the pressure inside of your lungs is actually lower. And then what happens, and that is what happens when you breathe in. So when you draw your lungs open, you just pushed all the O2 molecules out. So now you're creating empty space. And nature's like, look at all that empty space, right? And oxygen rushes into your lungs to fill that empty space. So I just make this joke, and I'm not trying to like make a political statement here, but like if you want to understand like nature under like hating gradients, nature is a socialist. Nature wants everybody to have the same amount of money, like wants everything to be nice and even. Again, that's not me trying to be political. Please don't fire me. But that's kind of an easy way to understand that. So during inspiration, right, during the inhaling portion, you have lower pressure. You have a big empty sac in your chest, and that is why air rushes in. And then when you exhale, you are squeezing that empty sac, and now it has very little space, and so there's just a bunch of oxygen molecules all clamoring into each other. So now they decide to all move and rush out of your lungs. So that's what barometric pressure. Barometric pressure is the amount of pressure found in the air, and then you have your intra-alveolar pressure, and that's the amount of pressure found inside of your lungs, okay? So in order for air to move into and out, we have to change those pressure levels. And luckily we have muscles that contract in order to like do that. You have control, right? If you go like this, you purposely just created a very low pressure area. That's why air rushed in. If you go like this, you created a high pressure area, which is why air wanted to naturally move out. So does that make sense to everybody? Anybody confused on that? Pretty good. That
Pretty
pressure.
good.
What's that?
Oh, I said good.
Okay, good. So that pressure concept's going to come back in just a little bit. It doesn't just happen on this big level. It also happens on the microscopic level. This is why O2 molecules either attach to your blood or don't attach to your blood. This is the same concept. So I want to make sure it's relatively clear. It's also why oxygen moves from the blood into your tissues. It's a pressure difference. Nothing can move without like pressure being the way it needs to be. So that's what ventilation is. It's bringing air into and out of your lungs. So for air to move out of the lungs, the pressure in the lungs must be greater than the pressure present in the air, okay? And this occurs because the diaphragm relaxes, which squeezes the lungs and creates a lack of space, okay? So that lack of space is, creates way more pressure, and then air rushes out. And then for air to move into the lungs, and actually I'm going to underline these. The pressure in the lungs must be less than the pressure present in the air. This occurs when the diaphragm contracts, which opens the lungs and draws air in. Okay. Must be less than that's what I'm looking for. Okay, so that's kind of how that works, right? And then we'll put it right here. Gases and other materials will always move to the area of low pressure. Okay, nature hates gradients. So we call that, when that's happening at your lungs, we call that external respiration. Okay, so this is all, when it's occurring like in your lungs, we refer to it as external respiration, because again, I know it seems kind of weird, but your lungs are technically outside your body, right? They are the outside environment. That's why this is external respiration. But then we also have internal respiration. Internal respiration is where you are exchanging gases on a cellular level. So if like air is moving into a cell, right, that is a respiration, that's an exchange happening inside the body, right? That's happening in your blood. So the respiratory exchange of oxygen and carbon dioxide at a tissue level, we refer to that as internal respiration. So we kind of have to look at that here. So external respiration, right? We'll kind of go back here. External respiration is the exchange of oxygen and carbon dioxide between the lungs and the atmosphere. Okay, so like at the lungs versus like the room you're standing in or outside, right? So oxygen enters the bloodstream and CO2 exits the bloodstream. Okay, that's what's happening at external respiration. And again, it's taking place at the lungs. Okay, and then we have internal respiration, which is the exchange of oxygen and carbon dioxide between the tissues of the body and the blood. Okay, and so that is going to be oxygen enters this exits the bloodstream into our cells, and CO2 exits the cells into the bloodstream. Okay? This takes place at the body's tissues. And that is the difference between internal and external respiration. But they're both examples of the same exact thing, like the process of like driving air in these different directions, like that is basically the same. The reason you need to breathe is because your cells need to breathe. And that's where we get the term cellular respiration. Cellular respiration is now that like that blood cell has dropped off some O2 molecules, and whatever cell is trying to keep alive, that cell's like, great, some oxygen just got delivered, right? And then it's going to take that oxygen in through its cell walls, and it's going to bring it to the mitochondria, and then the mitochondria is going to use that to produce a little bit of ATP, and Now you're left with a little bit of carbon left over from the glucose molecule that it also consumed. So it consumed a little bit of oxygen, it consumed a little bit of glucose, and now it's got the wreckage of that oxygen molecule, and it's got the wreckage of the carbon molecules from the carbohydrate, and it's going to combine them together into a molecule called CO2, and that's going to get, and then the cell's like, great, I'm done with it. It's going to push it out, and that CO2 is going to leave the cell. The red blood cell is going to pick it up, and it's going to carry it back to your lungs, and you are going to exhale that CO2 into the atmosphere. That is sort of like what we're talking about. Now, ventilation is going to be broken into a couple different sections here. Wrong bodies. So now ventilation is going to be broken into two main sections. You've got inspiration and expiration. So the mechanics of ventilation or breathing, right? Let's talk about what that means. You've got inspiration, right, which is the process of driving air into the lungs, right? And so inspiration is going to be begins with the contraction of the diaphragm. Now, just really quickly, again, I've already kind of talked about the diaphragm, but again, the diaphragm, which I always have a hard time typing, is going to be a dome-shaped muscle that relaxes to drive air out of the lungs, or contracts and to flatten down and drive air into the lungs. Okay, so your diaphragm kind of looks like this. Like I said, when it's relaxed, it's in this big kind of dome shape here, but it can flatten down when it contracts. Diaphragm contract. And there we go, that's the chart I want. So it's in this kind of big dome shape when it's relaxed, and then it will contract to flatten down in this direction here towards your stomach. And that's actually why when they say like you should breathe from your diaphragm, they're talking about like breathing like that. You're trying to, your stomach should pooch out a little bit because it is, you know, pushing downwards this way. So that's sort of what we're talking about when we say like a diaphragmatic contraction. That's also kind of what hiccups are. Hiccups are basically when your diaphragm is kind of spasming. It's doing these like big contractions. External respiration, again, and there's also intra-alveolar pressure. So the external respiration is like the exchange of gases in the air with your alveoli. That's taking place at your lungs, and then your intra-alveolar pressure, there's actually a pressure gradient where all those oxygen molecules, like, you know, now you've saturated the inside of your lungs with all these air molecules, and you've got all these blood vessels that are there to pick it up, and your blood cells are there to like pick up that oxygen. Well, luckily, the pressure, the amount of air found in your blood cells when it's at the lungs is actually pretty low. There's not very much air in your blood. There's a lot of CO2 in your blood. And again, nature being that it hates gradients is going to go, okay, well, I'm going to move these air molecules into the blood, and I'm going to move these CO2 molecules out of the blood. And that's going to change that pressure. And then, so when this pressure, and then this is just describing like air moving. When the pressure is less than the atmospheric pressure, air will move into the alveoli. And then the opposite is the other direction. When the air pressure is greater than the atmosphere, air will move out of the alveoli. We kind of already broke that down up here. We also have, if we have inspiration, we have to have expiration, right? This is the process of driving air out of the lungs, and this occurs with the relaxation of the diaphragm. So when you relax, this drives the air out. And so this begins with the relaxation of the diaphragm and the relaxation of what are called your external intercostals. And so your intercostals are, this is such a small picture. Your intercostals are all of these little tiny muscles that are actually between your ribs. So you've got your abs here, right? And you've got your obliques down here. And then all of these little tiny muscles that can be found in between each of your ribs, those are called your intercostals. And they also perform a little bit of that relaxing, which contracts. That actually kind of opens up or moves down, either opens up or closes down your rib cage. So you've got internal and external intercostals, which will sort of assist with that motion. So obviously when we breathe in, that also lifts up our rib cage a little bit. And that is a really good thing, but the problem is we start to rely on our intercostals muscles a little bit too much. Sometimes we'll even rely on our sternocleidomastoid right here, right? That muscle that is primarily responsible for like driving your head forward like this. That actually lifts up your collarbone a little bit. That's the cleido and sternocleidomastoid. It lifts up your collarbone, which again kind of lifts that rib cage and makes it easier for you to breathe in. All of that is something that we want to happen. Like, don't get me wrong. I love the intercostal muscles. I love my sternocleidomastoid. I'm glad I got them. I'm glad I got my obliques too. Your obliques are also going to help with that a little bit. But the problem is those muscles often become overactive because they do other things as well. Do you guys remember, for those of you who have been through our kinesiology class, the more actions a muscle has, the more likely it is to become overactive. That's why the lats are they're on our bad guy list all the time. You know, we love our lats. We love them, right? But they are constantly on the list of overactive muscles because it just does so much. It does adduction and extension and internal rotation, does all this stuff. Well, your sternocleidomastoid is primarily meant to like move your head like Quagmire, right? But like it also does a little bit of lifting of that clavicle there, which is important for things like raising your arm and stuff. So it's there to like kind of stabilize all this. And it does kind of help with breathing a little bit. So because this often becomes overactive, because those intercostals become overactive, and maybe sometimes even your oblique muscles become overactive, what ends up happening is your diaphragm weakens. It's the same overactive, underactive concept that we normally talk about. Like an overactive muscle takes over and an underactive muscle can't do its job. So now you're using all these secondary respiratory muscles instead of your primary respiratory muscles. And what happens is that actually decreases your lungs' ability to generate these big pressure changes. You end up doing these little tiny shallow breathing. Start breathing like this. See how I'm like moving my chest a lot? I'm like, right? Like there's a lot of stuff going on up here, but there's not as much stuff going down here. I'm not breathing with my diaphragm. I'm breathing with my upper body, right? And that causes you to actually experience like hormonal changes because you're not bringing in oxygen effectively. So your body thinks that it's just not getting enough oxygen. So then it starts stressing. So it creates stress hormones. And eventually, if that happens, you end up with an actual panic attack. And that is caused by like these little tiny shallow breathing patterns. And that's why we kind of, you know, we see it in like movies and TV, but you also see it when somebody actually panics. They breathe like really shallow, like that's why, like, you know, if you want to like look stressed out, just breathe like that for a little while and you will set the whole room on edge, you know? You know, that is very much caused, and those are all going to contract during the expiration process. The inspiration process is primarily your diaphragm, but when those secondary muscles start to work, they start to keep your diaphragm from being able to do its job. So obviously this is really important, right? We need to understand that, like, you know, the main reason we want these muscles to work the way we want them to work is because we need to have the right amount of pressure changes. And if you can't have those pressure changes, you're not going to be able to like actually effectively breathe. So speaking of pressure changes, at the end of a normal respiration, at the end of normal respiration, so at the end of a normal like exhale, right? Your intrapleural pressure, so the pressure inside of your lungs, within your pleural sacs, right, your alveoli, is less than the barometric pressure. So when you exhale, now there is very little pressure in your lungs, which nature is like, oh, awesome, I want to send all the oxygen over to the low pressure area. That's great, right? And so what intrapleural pressure is, it is an actual or potential space between what is called your pleural membrane, and that's what covers your actual lungs, versus the somatic pleural lining of your wall. So this is where we actually need to understand, like, there is a little bit of space. I think I get don't I get a picture here? I think I have a different class. We talk about this again in the next mod. I think I'm thinking of that class. Interpleural space. So when you look at like the amount of space inside of your lungs, that's a good one. Oh, I hate the clear backgrounds. That'll work. There we go. This is really good. I know it's. Susan? Oh, it's already zoomed in. All right, we'll kind of zoom in again. All right, I know this is kind of low quality, but I'm having trouble finding this type of picture I kind of need here. So take a look here. You can see like the atmospheric pressure, right? So like look, there's some space here, so the lungs can kind of open up and fill that space. Now you're gonna see this lining right here. See this little like empty space right here? That is your pleural cavity, right? This little bit of space between here and here, and this is your actual like pleura. So has anybody in here ever heard of like what is called pleurisy? Have you ever heard of pleurisy?
No.
Now it'll happen sometimes.
When it collapses, when there's air in there?
Kind of, yeah, kind of. It's where it can, I mean, that can be like a symptom of having pleurisy, right? So like what can happen is basically this pleural lining here can sometimes get like infected and get filled with water. When we think of water as like really slick, right? I mean, like we use water to wash our hands, but water is not as slick as something like soap, right? Like soap is really slick, right? Well, even more so than that, you know what's super slick? Mucus. Mucus is this like super visceral material that's like really, really slick. And so like there's a lot of mucus in between like all of your individual ribs and like your actual lungs. And that's a really good thing because we don't want our lungs to get stuck to our heart when our heart contracts, or maybe it would keep our heart from contracting. We certainly don't want that to happen. But we also don't want it to get stuck to the outside of our rib cage. So if you get an infection that causes like, and like that's what your body often does whenever something gets, you know, your body's like, I don't know, put some water around it, you know? And it drives water in here, that actually reduces the viscous like properties of your lungs. And so it starts to get stuck. And it makes it very, very, very difficult to breathe. That's a big part of like also what this disease does, right? This disease that we're all kind of dealing with right now is actually kind of related to what we're talking about here. It reduces your lungs' ability to move properly because it literally gets sticky. And that's not something we want to have happen. That's what pleurisy. I actually had like a pleural lining infection a couple years ago. I had like a regular old cold. And the ultimate field that I used to play on was nothing but dirt. The old field that we used to play on was like, it used to be grass, and then between like us playing and then the soccer game that takes place after us, we just destroyed this poor field. And so like, we were always like, I remember going home, this is too much information. But I remember going home and like taking a shower, and I would always have like this is so gross, but I would always like blow my nose and just black, you know, like dirt coming out, because it was just so much like dirt being kicked up in the air when I'd play on Saturdays. And like that actually caused, like I played Ultimate like way too close to you know, having like a regular common cold, and like that brought bacteria into my lungs, and then it got like infected, and I had to have like go on antibiotics because I had like a pleural infection. And it was super difficult to breathe because it felt like I was trying to breathe in, but like my lungs just wouldn't expand the way they were supposed to. And so I just couldn't bring as much gas as I needed to into that environment. And so you have to have like that pleural lining be plenty like slick in order for you to be able to expand your lungs. So again, this all kind of comes back down to pressure changes, right? So during expiration, your intercostals contract, your interpleural pressure increases, and so now there's a whole bunch of pressure in your lungs, and so all that gas is going to be ejected from your lungs. All that gas is going to go, that's it, I'm leaving. There's way too much pressure in here. I want to be outside of the lungs. And so as long as that barometric pressure is lower, that's going to happen. So airflow is going to move down that pressure gradient. Everything always wants to move down a pressure gradient, right? So when you think of a pressure gradient, what I want you to think of, like when I say what a gradient is, I want you to picture kind of a triangle. Oh, come on, just give me a simple, ugh, gross. Ah, there we go. Not quite a triangle, but like high pressure, low pressure, right? Picture a triangle, it's kind of moving this way. Picture sliding downhill, right? That's what a gradient is. And so there we go. That's actually a good one as well. Yep, right? It's gonna slide down the gradient. So that's where that is officially driving. So obviously I've been talking about pressure all day today, and we're not even done yet. We're gonna keep talking about pressure. But the reason we're talking about it right now, we're talking about gas exchange, right? Areas of high to areas of low. But there's also obviously things that affect these respiratory volumes, you know? And so your respiratory volumes are, you know, how much space you can create within your lungs. If you have a big body, you need to be able to create a big amount of space in order to like bring in enough oxygen to supply your tissues. So there's a lot of the big primary factors that are going to determine how large your lungs are going to be everything from your age. As we get older, our ability to contract and relax decreases because our muscles, you know, lose strength. Gender is going to be a big part of that, right? Obviously, like men tend to have like larger bodies, and so there's going to be a little bit of a larger capacity there. And that's related directly to body size. Now, you can obviously change your body size over time. If you gain a bunch of weight, for instance, like you have more tissue, but like your respiratory capacity might change. Bodybuilders deal with this, but also like obese people deal with this. If you've ever heard of sleep apnea is where somebody will stop breathing in the middle of the night, and it's often associated with obesity, although it can also be associated with like being just a really large-bodied like bodybuilder. Basically, if you have a heavy body, and what happens is like there's just so much weight pressing down on your chest because you get so much tissue here that it makes it hard for you to expand your rib cage. And so you'll be in the middle of the night, you'll be breathing normally, and then all of a sudden like your muscle, you know, you're in a state of sleep, and so your body kind of relaxes to a state where it doesn't contract hard enough. And so, you know, the diaphragm tries to contract, but it doesn't really try all that hard. And so then you don't breathe, and all of a sudden what you'll see with somebody who has sleep apnea is they'll just stop breathing. And they'll have this like really big moment where they just do a super large inhale, and it's kind of scary when you see it. And that big inhale is basically where the body was finally like, hey, diaphragm, do your job. Diaphragm. And I was like, diaphragm, and your body goes, what is what big giant inhale, right? And that is basically sleep apnea, and it makes it very difficult for you to sleep. And here's what sucks. That difficult to sleep makes it very hard for you to produce all the proper hormones that you're supposed to create. And so then you start making stress hormones, and then the stress hormones cause you to gain weight, and that gaining weight causes you to then have more sleep apnea. And it's a really kind of vicious cycle. But then another one that can affect your lung volume is your physical conditioning. If you strengthen all of the muscles throughout your body, you do cardio regularly, you get better at contracting your diaphragm and relaxing your diaphragm, you get better at driving air into and out of your lungs. That can change your lung volumes. That can make it easier for you to draw massive amounts of air into and out of your lungs. So let's go ahead and look at like how training our clients can actually affect those pulmonary volumes. So your lung volumes, we got a couple different volumes here. These terms honestly don't come up all that often, but in case this becomes something that you are actually measuring, like maybe in a lab setting, we'll go ahead and mention. So our different lung volumes, we got a couple different versions here. These are the volumes of air associated with the different phases of the respiratory cycle. So these are the lung volumes that are associated with like the different parts of like breathing in or breathing out, right? And so we have like the beginning of a breathing process and the ending of a process, and the pressures throughout them are very, very different because the volumes are different throughout them. So your inspiratory reserve volume, I'm only gonna put like the really important ones here because they're all of these, but I'm gonna pull up do I get a picture? No. This PowerPoint is bereft of pictures. It requires lots of Googling. Respiratory volumes. There we go. Okay, so this chart right here has a clear background. This chart right here, this has math in it. Don't pay attention to these formulas. But these are your different respiratory volumes, okay? So you have what is called your maximal inspiratory reserve, okay? Or your IRV. And this is basically the maximal amount of space that you have when you do, like, in order to, like, breathe in. So, like, imagine going like this. And then do it again. A little more. Like, eventually you're trying to, oh, God. I don't use my maximal respiratory inspiration. I don't use my inspiratory reserve volume all that often. So, like, I just stretch my lungs like crazy, and so almost caused me to cough. So that's your maximal inspiratory reserve. It's the maximal amount of space that you could possibly bring air into your lungs, okay? Now you also have like your reserve volume, right? Which is like all the way the exact opposite of that. Now, this is not something that you ever actually really tap into. But you got to remember, like when you try to exhale, you're like, right? Like, oh God, right? Like that's about as low as I can go. It's still like an empty, there's still a little bit of space there, right? But I don't really like have the ability to contract anymore. I can't really breathe any of that other space out. It's kind of like if you were to take a sack and crumple it up, you know, there's still like little bits of space in there. You got to really squeeze to get that out. There's always going to be a little bit of space left. That is like your reserve volume, right? But there's also your normal. So that's your inspiratory reserve. There's your expiratory reserve. So this is basically your maximal inhale, your expiratory reserve. That's your maximal exhale. So we're constantly like seeing those really large versions, but that's not how we actually breathe, right? Like the way we normally breathe, we have just a normal, what we call quiet breathing. That is referred to as your tidal volume, okay? Because it's kind of like breathing in and breathing out. It's kind of like the tide, right? It really is. Like when I say tidal, I don't mean title. It's tidal volume, right? It's the breathing in and breathing out normally. We call that quiet breathing. And that volume is right in here. Obviously, you could breathe in more. Obviously, you could exhale more. But these are those different volumes there, okay? So as we exercise, we tap into our maximal expiratory and our maximal inspiratory volumes. We tap into both of those while we're exercising. So as you start to like do more work, your body's like, holy cow, we are using oxygen like crazy. We need to bring in more O2 molecules. So it has you start breathing in more, and it causes you to breathe out more as well, so you can drive all that excess gas out of your lungs. And so that's sort of like the volumes that we tap into. So your lung volumes are all those different ones. So you have your inspiratory, I guess I will put these in here. So inspiratory, reserve, volume. Okay. Actually, you know what? Let's start with tidal volume. I know it's a tidal volume is technically later on in this list, but that's the most important one. So we'll start with that, and that's kind of where breathing starts. So tidal volume is the volume of air during normal, what we call quiet breathing, okay? So this is normal breathing patterns in and out. Sounds like the tide, right? So that's how we know tidal volume. But then you have your inspiratory reserve, okay, which is the maximal amount of air that can be drawn into the lungs after normal respiration. Okay, so like this is the total amount of air that can be drawn into your lungs after a normal breathing volume, right? So it's the amount of space left. Okay, so it's the amount of space left after tidal volume. Okay, then you have your expiratory reserve, which is the exact opposite concept, right? That's the maximal volume of air that can be expelled after normal expiration, right? And so that's the amount of space left after, I'm sorry, the amount of space available after tidal volume. And then you have like what's called your vital capacity, and that's all of it put together. That's the greatest amount of air possible that can be inhaled or exhaled after maximal. Actually, we can just leave it at that. So vital capacity is all of it. So if we look at this, right, you've got your inspiratory reserve, your expiratory reserve, and then the amount of space between this whole thing, that's your vital capacity. So how big can you make your lungs? That's your vital capacity. How small can you make your lungs? That's your vital capacity. The two of those things together. And then there is like that residual volume. Residual volume is any of the, like the space, like I mentioned, like the crumpled sac. Technically, if you were to take a vice to your lungs, and or like if you were to take your lungs out and like squeeze them physically, right, that'd be like your reserve volume. It's important to know for like medical officials, but like not really relevant to us. So we're not going to put that one here. Now, that's all about your minute. That's all about like your lungs volumes. But now, what about like when we're tracking this? Why don't we talk a little bit about like the idea of actually breathing, right? Like how often do you actually breathe per minute? How much gas is being drawn into your lungs every minute, right? Now, for those of you who've taken like our other classes, we've talked about like our heart rate and our stroke volume and things like that, right? Your heart rate is how many beats per minute. Your stroke volume is the amount of blood pumped per beat. And the two of those things coming together are what make up how much blood you are actually pumping throughout your body every single minute. Well, the same thing is true of ventilation. Your minute ventilation is the volume of air that you expire every minute. So the larger the body and the larger the lungs, the greater the minute ventilation, right? Because there's more space and, you know, probably breathing at the same rate as somebody else. So minute ventilation is going to be the volume of air inspired or expired per minute, okay? It is a product of your tidal volume, right? It is a product of tidal volume and frequency of breaths. So how much space is there and how much, oh God. Sorry, my mouse is acting funny. How much space is there and, you know, how many times are you actually breathing? So when we're talking about like gas exchange, right? Again, we kind of going all the way. So now let's kind of go back to the beginning and look again at gas exchange here. Gas exchange takes place in two places, right? We've already kind of talked about this. It takes place between your alveoli, so that's in the lungs, and your blood vessels, so those are your pulmonary capillaries. And then the other takes place is all of the rest of your body tissues and, you know, your systemic capillaries, right? All the capillaries throughout your body. So, so now we're actually talking about gas exchange. So we've talked about how to like bring air in. Now we need to talk about like how we actually trade oxygen in either places, right? So gas exchange will just kind of be our section header here. Okay, so the first place that's going to take place is at your lungs and your pulmonary capillaries, right? So at the lungs, gas exchange occurs between the alveoli, right? Those tiny sacs, and the pulmonary, we'll do this, pulmonary capillaries. Okay, what are pulmonary capillaries? are microscopic blood vessels that form beds to cover the alveoli. So that is where the actual, so what's going to happen is oxygen from the lungs will diffuse into the blood, and carbon dioxide from the blood will diffuse into the lungs. So oxygen, oxygen from the lungs will diffuse into the blood cells, and CO2 from the blood cells will diffuse into the lungs. Okay, so there's an exchange there, right? You give me oxygen, I'll give you CO2. Now, when you're at a high metabolic state, so like when you're exercising or doing any type of physical activity, the amount of oxygen you need in order to supply those muscles with the fuel in order to produce ATP, the need for that goes up. So what's going to happen is your body will sense that it's in a very, like your blood is going to, your body's going to sense that your blood doesn't carry as much oxygen. It's actually using all that oxygen up. And so it's filling with lactic acid and filling with carbon dioxide. And that's going to run by special receptors throughout your body that will trigger you to start breathing more. So your body will go, I always think of it this way. Your body goes like, there's special receptors and it's like tasting your blood. It's like, oh man, that's some lactic acid taste in blood. We need to start breathing more. And that's literally how cardio like enhances your breathing rate, is when your heart rate and breathing rate both go up because your blood became more acidic. There was more byproduct in your blood than there was oxygen. And that's also what triggers, like now your body knows where to like send that blood to, by the way. And this is on the cardiovascular side of things, but like that's what tells your body to go, all right, well, I'm not getting very acidic blood from the digestive system, but I'm getting super acidic blood from the glutes and quads. We must be running. So what it'll do is it will open up blood vessels to the glutes and quads, and it will close down the blood vessels to your digestive system. And that's what allows you to have greater oxygen delivery to the tissues that need it and less oxygen delivery to the tissues that don't need it. That's why you don't usually have to go to the bathroom that bad when you're exercising, because your digestive system kind of shuts down for a little while. I mean, it's obviously still getting some oxygen because it's alive. But like for the most part, like exercise drives oxygen to the areas that need it. And that's also why you get super hungry after a workout, because then all that blood flow returns to normal and the system starts up again. So, you know, I've been talking about like delivering oxygen all freaking day. How the heck do we actually get oxygen onto our blood cells? Like, how is it, like, we know that blood is what carries oxygen throughout the body. How the heck does that actually happen? Well, your blood cells have a special protein in them, okay? If we look at this, we got to understand there's this special protein inside of our red blood cells called hemoglobin, okay? And hemoglobin is a protein that contains a molecule of iron, okay, and is used, that's so funny, this, I must have just used this definition so many times because I wasn't reading this and I'm saying almost the same thing. It's a protein in red blood cells that contains iron molecules and is used to carry oxygen, okay? So here's what's kind of cool. Iron and oxygen, two totally separate molecules, but they get along really well. They like to kind of bind together. Like iron molecules and oxygen molecules really like to bind together. So we look at like iron as an element, right? This is what it looks like. This is like iron in its like hard form, right? Now you'll notice like it's kind of metallic colored, right? It's very silver. But then look at this version right here. This iron is kind of reddish colored, right? And that's because this iron has rusted, okay? And what rusting is it's the oxidation of iron molecules. So when you leave, like, if you've got like a cast iron pan and you leave water on it, it will start to rust. And what that is like that water, which has like oxygen molecules in it, is allowing more oxygen molecules to be attracted to that cast iron pan. And it's causing those to have like a chemical reaction together, and it's oxidizing the iron molecules, causing it to turn bright red. This is why your blood is red. This is what gives our blood the color red, is because of the iron inside of our blood. So what's kind of funny here, you always hear people say, oh, okay, so that's why my blood is red when it has lots of oxygen in it, but it's blue when it doesn't have any oxygen in it. So for the record, we need to dispel that myth right now. You never have blue blood. There is no such thing inside the human body as blood that is ever blue. You either have super bright red blood, which is like blood that is super rich in oxygen, or you have super, super, super dark red blood, which is blood that is rich in carbon dioxide. It has very little oxygen in it. But when you take that super dark red color and you mix it with the pigments in our skin, it kind of comes together to make this kind of bluish looking color. So we perceive it, like we look at it and we're like, okay, yeah, I got blue veins, right? Well, veins are deoxygenated blood. That's dark red. It may look blue, but you never have blue blood. Now, it is possible to have blue blood, but not for humans. This is always very hard. It took me forever to find this the last time I did this. Starfish blood. Yeah, nobody's gonna put a picture of a bleeding starfish on Google, which is a good thing. But for the record, starfish blood actually is blue. And that's because they don't use iron to carry oxygen molecules. Oxygen's also relatively attracted to copper. And copper, when it oxidizes, turns a bluish greenish color. And that's why starfish blood actually is blue. But human blood is always red because we use iron. Starfish use copper, humans use iron. Copper turns blue. That's actually also why the Statue of Liberty is bluish, right? Statue of Liberty is made of copper. It's supposed to look like this. It's supposed to look like a penny. But instead, it looks like a penny that you left at the bottom of a drawer for 6 years, and boom, it's this color. So, and that's starfish blood versus a cast iron pan that's rusty versus human blood. I'm way off the track on Analogy City right now. I need to get back to regular. So, hemoglobin, right? Hemoglobin is a protein. And it contains iron molecules. That's what carries blood. So men and women have slightly different concentrations here. In men, for every 100 milliliters of blood, we have an average of about 15 grams of hemoglobin. Women have just a little bit less with 13 grams of hemoglobin. So women do tend to have less hemoglobin. Ladies, this is why you tend to get a little colder easier than men do. We're a little better at carrying oxygen because of the higher levels of iron in our blood. And so that makes it a little bit easier for us to do like cellular respiration, which we know like results in ATP production, which results in like a little bit of heat. And remember, like ATP creates a bunch of energy. Most of that energy gets trapped by our cells to do work. Some of it leaks away and that heats us up. So that's why guys will complain about the room being hot, and their girlfriend will complain about the room being cold. For the record, both of you are right. It is a metabolic thing.
Oh man, guess I'm gonna replay this and record it and play it again and again.
Totally. Yeah, right. Like that's the thing. Like neither is right, neither is wrong. It is literally a physiologic difference. So arguing about it is silly. You just both need to be aware of each other's needs, me included. So there are slight different concentrations. This is also why women tend to be a little more anemic more often than men do. For the record, both sexes can absolutely be anemic. If I were to have a diet that is super low in iron, eventually I would become anemic. Now, there is also a little bit of difference here. Men do not experience, like due to like a lack of menstrual cycle, men don't experience like a loss of blood regularly. So there's not like a loss of iron regularly, which is why like anemia is also so common amongst women versus men. And that's also why if you look at like a women's multivitamin, it will often have iron in it. Whereas if you look at a men's multivitamin, it will not. In fact, if you give men iron as like a supplement, it can actually cause like a lot of problems, and their body will have too much iron in it. And so it will try to find ways to actually lose that blood. It will actually start shedding blood cells from the body in other ways, usually through like the stool and stuff. So anyway, so that's like kind of a difference there. There's a concentration of iron, okay? So there is something which is called hemoglobin saturation. This is the extent at which hemoglobin is attaching to those oxygen molecules. Now, here's what's kind of weird about this. This actually is kind of a hard process. Like, we're designed to do this. We are designed to have hemoglobin attached to oxygen, and we're designed to have hemoglobin also attached to carbon dioxide. But what's kind of interesting about it is it's not very easy at first. So when there's a high concentration of carbon dioxide on a red blood cell and there's no oxygen, what we want to have happen is we want to have the CO2 leave and the O2 join up, right? But that first oxygen molecule kind of has a hard time attaching to that protein. But one of the other things that's interesting about proteins is when anything attaches itself to a protein, it encourages that protein to change its shape slightly. And that's true of all proteins in the body, by the way. This is why ATP production works. Remember the ATP synthase, that ATPase little protein for the electron transport chain? The reason it's able to do that is because it has a little bit of a hard time at first, and then something attaches to it, it changes its shape slightly, and then it makes the rest of it very easy. This is true of all proteins. Whenever something binds to it, it encourages that protein to change shape. So the first oxygen molecule has a really hard time binding. But then once it finally does, it changes shape, and now that blood cell is more likely to pick up more oxygen molecules, and more, until eventually it's very, very, very saturated, and it can't carry anymore. Then it gets to your body's tissues, where it is encouraged to drop off that first oxygen molecule, which it kind of has a hard time doing. But then eventually it drops off the first oxygen molecule. That makes it a little easier, and it drops off another one. That makes it a little easier, so it changes shape. Now, that shape changing, we just talked about oxygen, that is also occurring with CO2. So now, because of that shape change, CO2 is likely to attach, change shape, more likely to grab more CO2, continues to change shape. Now it's really good at picking up CO2. So depending on where your blood cell is, it's either really good at picking up oxygen or it's really good at picking up CO2. And the levels of CO2 and the levels of oxygen present help both of those things occur. Now, this is what's kind of weird when we talk about this. This is what always kind of surprises people. Well, earlier we were talking about panic attacks, right? We were talking about where somebody feels like they can't breathe and they get really short of breath and they start to get really stressed out and they start to go into like a full-blown panic attack. Now, what you would think that is, and what people will describe is they'll say, I feel like I can't breathe, right? That's what they feel. They feel like they cannot breathe. What's weird is you would say, oh, if you can't breathe, you need more oxygen, right? Like that's what makes sense. That is actually not the problem. When somebody is having a panic attack, what they're actually suffering from is a lack of not oxygen, but a lack of CO2. They are actually too low on their carbon dioxide levels. And that seems really opposite. It's like, wait, why do they feel if they can't breathe? I thought CO2 is the thing we exhale, and that is true, but remember, CO2 unbinding from a protein molecule changes its shape and allows oxygen to bind. So when you are having a panic attack, what helps with that is breathing into a paper bag, right? So you breathe into the paper bag And all the CO2 that you do exhale leaves your lungs, but it gets trapped in that bag. And then you inhale from the paper bag and you reintroduce all that CO2. Your body continues producing ATP the way it normally does, burning up. And then, you exhaled some oxygen, right, into that bag as well. And then that oxygen came back in, and you're living off of that oxygen. But because you inhaled some more of your CO2, your levels, which were super far apart, are now getting a little bit closer together. So you burn up more oxygen, exhale more CO2. Now, if you were to keep breathing in that bag, eventually you would have no oxygen in there and you would, pass out or something. But that is actually helping your CO2 levels return back to normal. And that's why breathing into a paper bag helps. And this can happen in athletics. This is why we're talking about this. Shortness of breath and panic attacks can sometimes happen to athletes. They can sometimes happen to your clients because if they have really poor breathing patterns, it'll usually happen to your clients who have posture like this. It'll often happen to those people who have really rounded shoulders and really elevated shoulders and a super forward head posture. Those people tend to suffer from panic attacks more often than people who don't. And the reason why is because of their poor posture. It causes shallow breathing patterns, and it causes them to exhale too much CO2 whenever they breathe. They breathe shallow breathing patterns, and it actually causes them to vent carbon dioxide too much. I know we want to get rid of carbon dioxide. That is true, and that's going to remain true. We want to bring in oxygen and get rid of CO2, but we don't want to get rid of all of the CO2, because if you get rid of all of it, it makes it harder for oxygen to bind, and then you'll feel like you don't have any oxygen. So you want to have proper posture so that you can breathe the way you're designed to breathe, so that you don't mess up the balance between CO2 and oxygen. And that's why, again, posture becomes so important. You wouldn't think that it has anything to do with chemistry, right? But posture is directly related to this chemistry concept. It makes the physics of binding oxygen and CO2, it makes it more difficult. And that's, kind of why we're actually talking about it. I always like to bring this up because sometimes it seems like, hey, this is a lot of we're talking a lot about the really small. How could this possibly be relevant to me showing somebody how to do squats? Sometimes it doesn't feel like this conversation is very relevant to what we do on the day to day. But when you're explaining to your client why it's so important for them to do their homework, why it's so important to draw their shoulders back, why it's so important to work on their upper back, even though that doesn't help you look that much better at the beach. Everybody wants their abs, right? We got to understand. It's look, it literally assists everything that you do. Everything that you do comes down to your ability to digest food and bring in oxygen. If you can't do this most important one very effectively, that's because of your posture. So hemoglobin is the protein that carries a molecule of iron in your red blood cells, right? And this is red blood cells are saturated with hemoglobin proteins, which is why red blood cells are responsible for carrying oxygen and CO2. Now, you've also got another protein that is also really important called myoglobin. For those of you who have been through our kinesiology class, you might remember me saying, anytime you see the word myo, we are in muscle territory. Well, your muscle cells have a special little protein in them called myoglobin. And it's a protein found in your muscle fibers that also binds and releases to oxygen. But its job is to carry oxygen molecules to your mitochondria. So for the most part, mitochondria lets just oxygen kind of float around in certain other tissues, like your fat cells, for instance, kind of just lets oxygen eventually reach, because fat tissue is a really low metabolic tissue. But because muscles eat oxygen so heavily and they eat it so quickly, your muscles need such an oxygen delivery. You have a special protein that makes sure that like once the oxygen is in the cell, myoglobin's like, oh, great, let's get that to the mitochondria, stat. And so it's like a delivery guy for your delivery guy. So it is a protein in muscle fibers that binds to oxygen and delivers it to the mitochondria. So this is a super oxygen-rich protein. It's found in cardiac muscle cells and skeletal muscle fiber cells, and it is especially found in type 1 or slow twitch fibers. So slow twitch, which we haven't really talked too much about yet, muscle fibers have higher levels of myoglobin, which make them better at utilizing oxygen. This is why they are your endurance muscle fibers, right? So when we label something fast twitch or slow twitch, we label it based on how it looks. Well, if it has more mitochondria and it has more myoglobin found inside of that type of muscle tissue, that is a slow twitch muscle fiber. It may not be able to create very much force compared to a fast twitch muscle fiber, but it can do it forever. So it helps with the delivery of oxygen to the mitochondria. Now, we have talked a little bit about carbon dioxide here. Now, not all of the carbon dioxide is directly carried by your red blood cells, by the way. Some of it is actually dissolved in your blood. So some of that carbon dioxide is just physically dissolved. So carbon dioxide is physically dissolved in your blood where it diffuses as it gets exhaled. So some of those carbon dioxide molecules may like stay whole and they get delivered and just, you know, exhaled. Some of it, once it reaches your blood, dissolves into individual pieces and is also then kind of gets exhaled by your lungs. But about 60% of it diffuses into what we call bicarbonate. And so about 60 of it diffuses and is transported with a little bit of combination of like sodium. And so that's where you get like what's called sodium bicarbonate. This is another reason why like maintaining your electrolyte balance is actually so important. Sodium is an electrolyte. You want to make sure you have some of that inside of your cells and inside of your blood so that it makes it easier for you to deliver oxygen. For instance, when you are like cramping up can be caused by a couple different things. Sometimes it can be caused by like your nervous system not effectively being able to contract, and so it squeezes and then it kind of gets stuck turned on. That's like a Charlie horse. Or sometimes you might experience cramping because like, you know, fluid levels are really low and your body can't deliver nutrients to those tissues. So then they can't contract the way they're supposed to. That can cause cramping. But sometimes it can also be caused by a lack of sodium, which is causing like carbon dioxide to build up in your muscles and causing like a cramping sensation. So cramping we have a lot of ways that we can start cramping up. And it's why it's such a common thing. By the way, here's carbon dioxide transport. Here's actually, you can kind of see that dissolving action. Finally, I got a freaking picture in the PowerPoint. So here's a red blood cell, right? And you can see like dissolved carbon dioxide can kind of just like naturally leave. But you can also see like it can be pumped through these special little proteins here and actually like exhale that way as well. So here's like the tissues of a wall, right? So like if you had a red blood cell here, and then like this is the tissue, CO2 can leave, while O2 can leave the cell and enter into the tissues, and CO2 can leave the tissues and enter into the cell. Then the exact opposite process would happen at the lungs. CO2 would leave as O2 enters. So there's a few things that are going to be here as well. Obviously, it takes time for this to happen. So that's what's called your diffusing capacity. Depending on how much hemoglobin or myoglobin you have, that's going to depend, or like depending on how much pressure there is in the atmosphere, that's going to help with like your diffusing capacity. So how quickly things are able to move. There's also transit time, which is literally how long it takes a red blood cell to get from point A to point B. You know, depending on how fast your heart is beating, that's going to affect how much pressure and, you know, affect how quickly your blood cells can travel from one place to another. So when you have like super high like workloads, your transit time can have like a negative effect on your performance. If you just don't have pressure, if you don't have like high pressure, which means that blood can't travel quickly, you might like lose performance. And that's why like when you're doing maximal strength lifting, your blood pressure skyrockets through the roof. You know, we think of normal blood pressure as like 120/80. Well, I think one of the highest recorded blood pressures was like mid deadlift on someone. What is the highest recorded blood pressure? What was it? It was like, yeah, 370/60. It's like you would think that like if 120/80 is normal blood pressure, you would think that like this would cause your freaking brain to explode. But that's why we see high pressure during deadlift. I just want to find a funny picture here. Funny picture, funny picture. Ah, I was hoping to see a picture of a guy who's like, looks like his head's gonna explode. It's probably like a picture of that. You can, yeah, you can see some veins there. You know, but that is what's happening, right? That's a good thing because that's affecting your transit time. Blood can be delivered like crazy when that's happening. So I'm just going to mention a few things that are going to help us remember that we're going to come back to in tomorrow's lecture. You do have oxygen delivery and cardiac output. Both of these things are going to affect your ability to deliver those gases. So oxygen delivery is the product of cardiac output, right? Cardiac output is the function of the heart. You can't deliver oxygen unless your heart is functioning properly. So that leads me to one last thing I want to talk about just before we leave, kind of going back to pressure here. And I know that, again, this is not like a political statement, but like you sometimes hear people say like, oh, I'm worried about not being able to wear my mask right now in this world because like I have a hard time breathing. The mask actually does not affect your ability to diffuse oxygen at all in any capacity, because you are at the same level in the world right now. It's not like you went to the top of Mount Everest. You're standing on the same place you were standing before you put your mask on. So your oxygen delivery utilization is exactly the same. This is also why those masks that are so popular, those training masks, O2 training mask, you guys ever see these? They sell them on the internet. They're really popular. I don't know what that was a picture of.
Oh my goodness.
Skip right
Yes.
past that. What the hell was that? Anyway, if you take a look here, right, you see these training masks, right? They're very popular. Actually, Maggie, you ever see anybody wear these like for the boxers?
Yeah, all the time.
Yeah. So here's the thing. These don't do what people think they do. And I'm sorry to kind of myth bust here. I'm sorry to like break things. I have students constantly accuse me of being a ruiner.
They don't do anything. They don't do anything.
They do
Yeah,
not.
I know I was gonna say, but it's
The only thing will work will be an actual elevation gain.
Exactly.
That's
You
the
nailed
only
it.
thing that will change.
And here's the reason why. I won't say they don't do anything. I will say they can be used to build mental toughness. It is really uncomfortable to wear these masks. And so like if you're trying to build like your mental toughness and you want to be able to like, you know, be in a situation where like you know, in a sport like fighting, like that is a mentally tough sport, you know. So like there's definitely like a little bit of benefit there. Like it's difficult feeling. This reduces how much gas enters your lungs. So this reduces, like, it's like breathing through a small straw. It reduces how much gas is entering your lungs. But remember, you're still at, I mean, we're in LA, we are at sea level, you know, like it's not a very high elevation place that we live, Los Angeles, you know. The amount of pressure in the difference of the atmosphere and in your lungs is the same here as it would be without the mask or on it, right? The concentration of oxygen molecules is the same. Yeah, you might be bringing in less volume of gas, but the concentration is the same with the mask on or with the mask off. And this is why it does not affect how much oxygen you can breathe in. It might affect how much gas you're filling your lungs with, which might feel psychologically uncomfortable, but it doesn't have any effect on your body's ability to drive oxygen into your blood cells, because that is barometric pressure. Now, if you go to like Mount Everest, there are less molecules of oxygen in the air. And that's why it is so difficult to breathe at high elevation. That's why they have to bring those oxygen tanks, because their body is actually not being able to bring in as many molecules because there are less molecules present. Now, what's kind of cool about that, what's really cool about being in a place like Everest is your body goes, holy crap, there are no oxygen molecules up here. All right, we need to get better at gathering oxygen molecules. So what it will do is your body will actually start producing more hemoglobin. Your body will make more hemoglobin, which makes it even better at grabbing oxygen. So if it is in a low oxygen environment, then what happens is you come back to the regular world and you're like, I'm so good at breathing right now because I have all this extra hemoglobin that I just built up. And now you can gather oxygen molecules. This is why like professional marathoners or professional runners will train at high elevation and then come back to the regular world. This does not affect your elevation. The concentration of oxygen molecules is the same. The only thing that will affect the concentration of oxygen molecules is going to a high elevation area. Now there's not as many oxygen molecules. Now your body will make more hemoglobin. This does not make you make more hemoglobin. This makes mental toughness, which is cool. I'm not saying it doesn't do anything, but I am saying it will not make you better at breathing. And that is also why wearing a mask in public, which is an important thing to do right now, it may feel uncomfortable. It is not affecting how much oxygen you can bring in at all. Doesn't affect it. The concentration of oxygen is exactly the same right now. I'd had this conversation with my mom recently. In summary, at the end of the day, I know we went through like a lot of kind of deep stuff today, and it feels very technical. This stuff is always hard because you can't see it, right? This is why studying metabolism is hard. You can't hold it, you can't touch it, but you've experienced this plenty of times, right? You've experienced pulmonary ventilation your whole life. But at the end of the day, the big thing I want you guys to know and the big thing to remember is like pressure changes are what's important here. You are opening your lungs by contracting your diaphragm. That creates low pressure. That's why air drives in. And then because there's a lot of O2 molecules in the air, but there's not a lot of O2 molecules in your blood, that's what causes it to move that way. So there's pressure in like the amount of gas, but there's also pressure in the amount of molecules, okay? Your muscles rely on oxygen. We need to be able to deliver oxygen to our cells in order for them to produce ATP. So we call that your aerobic capacity, right? So later on in this course, we're going to start getting into the differences between like, well, what happens when you burn all that oxygen up? Like what happens when you reach the maximum? What if I can't bring in any more oxygen? What happens if like I'm bringing in as much oxygen as possible and my body's using all of it? What happens then? Well, that's called your VO2 max. That's your volume of oxygen consumed max. There is a VO2 max for all of us. We all have a different VO2 max, but you can increase it through training. You can increase it by doing cardio. And what that does is that makes your body make more hemoglobin. You tell your body, holy crap, we are not good at consuming oxygen. You need to make more protein. You know? And your body goes, great. It doesn't make any more red blood cells, but it does make more hemoglobin within those red blood cells. So your body gets better at consuming more and more oxygen. The more oxygen you can consume, the better you will be at cardio. And that's where the second half of this course comes in, right? Like we're getting all the anatomy and physiology out of the way in the first half. We're getting how to train for it in the second half. And that's when we're going to do a whole day on cardio. And that's that today, guys. Really technical day. Arguably the most technical day. I mean, I don't know. Metabolism is pretty technical as well, so I don't want to say that. But Great work. Do you guys have any questions about any of this? Questions, comments, concerns? Erica, do you have a question? I mean, I'm asking
No.
you, I'm only asking you specifically because you don't normally get to ask, but you watch a lot of videos.
Yeah, I'm okay.
Damn. Anyone? How are you feeling?
Good.
I feel good. I feel like I had a silly question. That's why I'm like, should I ask that question? I feel like it's gonna come up later.
Questions are like, if you don't ask questions, then this lecture is the same as the next time, and I start to get bored. So.
Oh no, I was just thinking. I was just thinking about the breathing when doing actual exercise, because I know like in the past I've brought this up too, where you know, majority of the females tend to like hold in their breath. So just like being able to have a conversation about how the importance of breathing, but also the main question I had was when someone is performing a specific exercise, you know, there has to be a specific like inhale and exhale during whatever it is that you're doing.
Yep.
So that's
Yeah, this becomes part of, like I said, like the second half where we start talking about the cardio and how to train for it. We're gonna address this, but I'd love to bring it up today. That's great. I will say I don't think it's quite necessarily just a female thing. I think people just sometimes have a hard time breathing. I wouldn't say there's a gender difference there necessarily. At least not that I'm aware of. I could be totally wrong, actually.
No, yeah. I think it relates to like. Oh, sorry. Go ahead.
I don't think like are more common.
Yeah, no. It was only I only said it that way because it was in reference to like how women feel like, oh, I have a pooch now, so I have to like hold it in, and females tend to do that more.
Sure. Okay.
Like
Yeah.
like.
That is insightful. That actually, I don't know. Maybe that actually would be true. I bet that's one of those things that like isn't physiologic but is habit forming. I love. Oh man, we could launch off on this, and I don't want to like get too sidetracked, but I love looking at like the real reasons behind things sometimes. Like sometimes people think that's like, oh, it's because of this. And it's like that's not a gender. That's a habit thing. That's like here's a really weird thing. If you want to watch a really cool difference, and this is also like somewhat gender related, has, by the way, this is not a political statement, has nothing to do with like what I'm teaching today. If you want to watch a really cool episode of TV though, check out the show Explained and look at like the science. I think it's the science of women actually. And it's a really interesting thing. Or no, it's the science of the wage gap. And it looks at like why, like, you know, statistically men get paid more than women do. A lot of times people think that it comes from like a sexist place of like men just don't value women as much. That's not 100% likely the reason, but we have structurally designed the world to give like maternity leave, but not paternity leave. And so because we don't give men time off, we think of women as caretakers, even though men are just as good at it and women are just as good at like working. And so like, but we've structured our world this way. So then what ends up happening is it creates this huge difference between the two. And like men continue developing job skills and women get like stagnant for a brief period. And so it causes like a loss of like a change in the gap. And you look at the countries where they give women maternity leave and men paternity leave, and both parties are like equal members of like taking care of the kids, and like you see a much smaller gap between the way. Look at, it's a really cool episode, and like it's not necessarily like the first thing you think of, which is just that like one group is more sexist than the other. It's just that we designed this thing, we messed up the design, we put the IKEA furniture together wrong. Like, it's a structural problem, not a psychological problem. It's really cool. It's a really interesting episode. And don't get me wrong, I think there's also a psychological problem in some ways. I think that there is that as well. I think
that's interesting though.
Present, but I do think that like if you fix the structure, eventually like the other stuff happens naturally, you know? And so it's like, all right, fine, I can't change your opinion. I'll change the world. And now your opinion doesn't matter anymore, you know? Like, away, you know? If I can't you know, if I deal with my clients constantly where they're like, yeah, but I love ice cream. It's like, I can't change your love for ice cream, but if I can convince you not to keep it in the house anymore and you have to go to Baskin Robbins to get it, you're going to eat it less often, you know, because then you're going to be like,
Yes.
oh, I got to get in the car. And then you don't want to. And it's like, boom, you ate less, you know, like change the function, change the form. So I love that, Nancy. And I did sidetrack. I meant to keep that like one sentence. And here we are. Going back to your original question, are there specific ways to breathe? I'm going to give you the general rule of thumb, and then we'll address this more later in class. But general rule of thumb, whenever you are concentrically contracting something, exhale. Inhale whenever it's eccentric, exhale whenever it's concentric. So bicep curls, exhale, inhale, right? Bench press, exhale, inhale, exhale, inhale. Shoulder press, exhale, inhale. Exhale concentrically. Crunches, exhale, inhale. For the most part, keep it exhaling when you're concentric, inhaling when you're eccentric. That's a super helpful technique that will help you maintain proper blood pressure, and it'll enhance your breathing. The other side of it is there is one other technique that you can use to your advantage. Remember, we need pressure changes in order to drive oxygen effectively. There is a technique called the Valsalva maneuver, which is where you inhale and then you actually hold your breath and exhale through pursed lips. You go, and so you kind of exhale forcefully. That really contracts because you start using all those secondary muscles. That raises your blood pressure. So it's very helpful during compound lifts like the bench press, deadlift, and squat. But you never want to do that technique with somebody who already has like blood pressure problems. So there are techniques to be used. Yeah.
Okay. That being said, I had a question about that too. Like when you see like some like world like record holding lifters and stuff like that, and then they like hold their breath and like do their lift, and then sometimes they like pass out. Is that like due to not enough oxygen?
Yeah. So what they did, that's why they passed. Like Eddie Hall, he always like.
Yeah. Yep. Yeah. Exactly.
So like what that is when you contract like that, that breathing enhances your blood pressure, which pressure is now going to go to whatever muscles are being metabolically used the most, which in this case, since you're under tension, are all of the like the deadlift or the squat or whatever muscles, right? It's all the muscles like mid lift. The other nice thing is when you press like that, notice how like I go, you see how like my stomach pushed out, like it caused my core to like contract really hard. That's going to keep my spine protected because I'm creating so much pressure that my discs are less likely to slide around. So the Valsalva maneuver is really necessary in the world of powerlifting. The problem is because that's creating pressure where it needs to go, and now blood is like, well, I guess we'll only go to those muscles. All of a sudden your brain, which is like, hey, I still need oxygen too. Like,
yeah.
All of a sudden your body goes, it doesn't get any of the oxygen it needs, and so then you black out and pass out. That's also why if you've ever been like laying on the couch for a couple hours and then like you're just like, all right, I gotta get up, and you just like jump up, and then all of a sudden like the whole world goes dark.
Yeah.
You've been laying in a position, so your blood pressure is just super low because you're just not doing any work. And then all of a sudden you jumped up and you had no pressure to get blood back up to your brain. So you're standing over here, but your blood wants to be back on the couch. And that's why that's like you just don't have any, and so like the whole world kind of like disappears. That's what blacking out is. It's a lack of oxygen to your brain, and it's kind of a protective mechanism, you know. It's happening because it's actually your brain purposefully shutting it off because that will cause you to crumple and then lay down. And when you lay down, you're horizontal, and it's very easy for blood to travel like this versus gravity like this. So passing out is kind of a protective mechanism. That's also why people faint. Some people faint at the sight of blood. That's your brain going, is that our blood? Well, if it is, we must have low pressure. Lay down, and so they pass out. It's easy for stuff to travel this way versus gravity this way.
Okay.
Yeah.
I mean, there's also going to be conversation on, I'll probably like hold off, but like on breathing while running.
Yeah, that's a harder one. The consensus is that's not one. There's a lot of opinion floating around on that one. I'll give you my take on it, but there's not an official one I can give you. So you'll have to mine. It's like when we talk about shoes. You'll have to you'll have to accept like my opinion on it, but it'll definitely be very opinion based. But there is, the one thing that is not opinion is like you want to try to be as diaphragmatic when you're breathing while running as possible. Your rhythm, there's a lot of debate on what the proper breathing rhythm is. I like a 3-to-1 breathing, like 1, 2, 3, exhale, 1, 2, 3, exhale, like na 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 da 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 na na, like my get it out quickly. But it's a little different for everybody, so we'll look at that. But I'll definitely put an asterisk next to it. Anything else?
No.
Cool. Well, good job today, guys. That's another really technical one. Exercise quiz is brutal. Any of my new students who are watching, stay alive. Promise. We got a fun one. We got nutrition coming up in a couple days. All right, guys. I'm gonna let y'all go. I'll get Canvas. Congrats. We'll see you for day 4 tomorrow.
Thanks. Have a nice day.
Right.
You
See you
too.
guys.
Thank you, Brad.
Yeah.